Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Zach Murray with us today. Hello, Zach.
Hello.
Cool.
Hello, great to be here.
Well, thank you so much for agreeing to talk about your very lovely article, which we will get to very shortly. And Zach, what's your geolocation? Where are you at?
I'm currently out in Cambridge, Massachusetts.
Okay.
East Coast.
Yes. Is it summer and humid yet?
It's not too humid. I think we're still hanging on to spring as much as we can, but getting a little warmer slowly but surely.
Yeah, so it is May 17th, 2024 as we record this one. And I'm in Phoenix, and we are definitely into our warmer phases. Get some triple digits Fahrenheit. Sweet. So yeah, we are definitely toasty, very fall. And
a little warmer than in Boston.
Yeah. Yeah. And Zach, what's your position there in Boston?
I am currently a grad student, just finishing up, and I will be a postdoc here at the Smithsonian, most likely, in a few months.
Few months. Okay. Well, let me be the first to congratulate you, Dr. Zach. That's wonderful.
Appreciate it. Thank you.
Wonderful. And Dr. Zach, what do you like to do for research?
Well, I do a bunch of different things, but mostly I'm a dynamicist. I work on trying to figure out how planets and asteroids pull on each other as they fly through space in a bunch of different contexts, both here at home in our solar system and out in other solar systems with exoplanets.
Very cool. Very cool. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go get a copy for free. Go grab one. The effects of disk-induced apsidal precession on planets captured into mean motion resonance. And Zach, take us away.
Yes, indeed. So I wrote this article with the help of my co-authors, Sam Haddon and Matt Holman. Sam is currently up at CETA in Canada, and Matt's at the CFA.
Good shout out. Good shout out.
Yes, indeed. This is a pretty technical paper, so I wanted to start with a little bit of background.
Okay.
So, we have our typical situation and say the solar system, another exoplanetary system is you've got planets orbiting a star. Most of these systems are pretty flat. They're nearly coplanar.
Okay.
And so in this sort of paper, we've kind of taken this coplanarity and ran with it. As an axiom, our system is 2D. And the orbits here don't close. The orbits kind of move around in the direction of in the plane of the system over time. And that's kind of this apsidal precession we're talking about.
Okay.
So another way of saying this is how are the mean motion resonances these planets get captured into affected by that precession, that moving of the orbit?
Cool. I'm with you.
So I guess to start, I'll go kind of into the introduction, into these first in-text equations. We have this E is kind of proportional to tau E over tau A. We've got this definition of tau E, tau A, etc. This is all about...
Yes.
Yeah, you got the right equations. This is all about traditional resonant capture theory. The kind of notion is you have massive bodies, maybe forming in a protoplanetary disk of some sort. Could do this by tides as well. And they're migrating in the disk. The semi-major axes typically are decreasing, and there's some eccentricity damping. And so the orbits are becoming more circular over time due to their interactions with the disk.
Okay.
Now, when you have this sort of situation, something fun can happen. If the two planets migrate such in a way that their period ratios shrink, so they're kind of getting closer to each other.
Okay.
They don't go and smack into each other. They actually get caught before they smack into each other at some specific period ratio.
Okay.
So for example, the period of the inner planet might be 1, the outer planet might be 2. It's some simple integer always.
Right. Okay.
And those are these mean motion resonances.
Yes.
And they capture at very specific eccentricities. And that eccentricity, as you can see here, is just a function of these two time scales. One tells you how strong is the orbital circularization. The other's telling you how quickly are they migrating towards each other.
Yes. Okay.
And so it's kind of a very nice, simple toy problem. Was developed to kind of understand the configuration of the Galilean moons, but since then it's been applied to exoplanetary systems. We observe a lot of them. We know some of them are in resonance, and we think this is the physics behind it.
Cool.
And so that's where the kind of field was a few years back. This was published, I think, in 2022.
Yes.
So
yes.
This was the state maybe in 2020, 2021, that sort of time.
Okay.
And so that's where we begin. This is a great model, but one of the things it neglects is the fact that this disk that we invoked to perform this resonant capture, it has mass. It's not just damping the planet's eccentricities. It's not just causing them to migrate. It should be pulling on them too.
Right. And vice versa.
And vice versa, yeah. And that creates a problem. There's an old mathematical result that I love to start with these sorts of conversations. It's called Bertrand's theorem.
Okay.
We kind of all learned this maybe back in high school, undergrad, when we're doing our central force motion course.
Yes.
But as a reminder to all of us, if you have a central force motion and there's some potential controlling that motion, there's two and only two cases where the resulting motion is a closed orbit with no precession.
Okay.
One of those is gravity. The other is Hooke's law, so that things springs follow simple harmonic oscillators.
Okay. Yes.
So now we're considering a situation where we have gravity between these two planets attracting to the star.
Okay.
There's an additional radial force from the disk.
Okay.
According to Bertrand's theorem, that's no longer gravity alone, so there must be precession.
Okay. Nice.
That's where this Apsidal precession is coming from.
Cool. Okay.
So it's disk-induced.
Yes. Yes. That was cool. Good.
So now we have to actually do the physics here. Now we got to the hard part. That's our setup, though. We've got massive planet inducing precession, resulting in differences in the resonant capture process.
Yes. I'm with you.
Alrighty. So if we scroll down a little further, I'll jump all the way to equation 2.
Hamiltonian.
We get this kind of Hamiltonian model here. Got H, whole bunch of variables, and two precession rates at the end of it. That's this omega 1 dot and this omega 2 dot.
Okay.
So we've taken a few steps here. We've translated from, planets having forces on each other to this Hamiltonian model. All the variables look different because if you're doing Hamiltonian dynamics, you have to rescale everything. You can see this gamma is approximately like an eccentricity. This epsilon is kind of like a mass ratio. I'll just have you take my word for this, that this is correct.
Yeah, okay. I take your word for it. I take your word for it. I trust you. We're not going to fact check it right now.
Checking it is difficult. I had to do this a few years ago, and it took a little while.
Pencil and paper?
Pencil and paper, Mathematica, and a whole lot of coffee.
Yeah. Cheers
that
to
took
that.
a day or two
Cheers
to verify.
Very good. Yes, very cool.
But I'll claim without further mathematical rigor that this is the form of a Hamiltonian for a two-planet system with additional terms accounting for precession of the orbits.
Okay.
And so depending on the size of the disk you end up with, you're going to modify omega 1 and omega 2.
Yes.
Two terms, two planets, each can have its own precession rate.
Yes, good.
So that's all that's saying.
Okay.
Next thing we do is we invoke some migration forces. This is kind of in equations 3 and 4. Remember this gamma here is an eccentricity, so that should look relatively familiar. That's pretty much the same as traditional theory. And this P is just describing the distance between the planets, their period ratios.
Yep, right there. Yep.
So that's our equivalent of, this convergent migration scenario from traditional theory.
Yeah.
So the only thing that's really changed is these precession rates.
P. Yeah. Okay. Okay, good. I'm with you.
So that's our physical situation. And we kind of solve these equations out algebraically, and we end up in equation 7.
6 and
which is all the way down here, and I'll skip over the
the interested
page
reader,
of algebra.
will show that.
Yes. That is left as this question for the reader. I think is the expression.
Indeed.
And so we end up with this equilibrium eccentricity, just like we did in the unperturbed case, the non-precession case. That seems reasonable. But it's got a much more complicated form. It's not this, tau E over tau A. It's nothing simple. It seems to involve mass ratios, the eccentricity of the outer body, and then this delta omega additional. And that's just omega 1 dot minus omega 2 dot.
Okay.
So it's just the difference in the precession rates.
Yeah, that is a little more complicated.
Unfortunately. The interesting thing about this sort of equation, if you kind of stare at it long enough, that denominator could get rather small in certain cases, depending on the physical situation. And that's kind of the driving force of this paper. Are there kind of physical situations where you see a big enhancement in eccentricity due to a large, say, differential precession rate between the planets?
Yes. Good. Okay.
And so this is where we kind of begin to explore planetary work. So we're moving away from the math and going now into more physics.
Okay.
And so we consider kind of in this next paragraph, what sort of situation could lead to a blow up here.
Yes.
And we consider the case of 2 planets. They're orbiting a star interior to some massive disk.
Okay, interior.
Disk is axisymmetric, and we've assumed kind of a power law surface density profile.
Okay, sure.
This is pretty standard. It's done in kind of minimum mass solar nebula. It's done in disk theory.
Yes.
It's everyone's favorite simple model.
Because you can do something with it. Okay.
Yes, indeed. So we just state the equations for that density profile. That's kind of equations 8, 9, and then 10 just gives you the disk potential. So that's what the planets are feeling.
Okay. Yes. Okay. Got profiles, potentials.
Massive stuff.
Yeah. Good stuff.
And that leads us to figure 1. So we're still kind of in this hypothetical situation where you've got planets interior to a disk. And what we're showing you here is the precession rate in units of the mean motion for various disk geometries and power law indices. So we've got R out at 50 or 100. We're changing the power law index. And we're just showing the precession rate as a function of how close you are to that disk inner edge.
Okay, inner edge. Okay. Yep.
Keep in mind the planets are orbiting kind of interior to this massive disk.
Right.
So how close are you getting?
Okay.
And you can see we get a whole bunch of different results, depending on the geometry of the disk we consider.
Yeah.
If you're pretty far from the inner edge, you get something that looks kind of like a power law. That's what you'd expect. And as you get closer, there's this, very quick enhancement.
Right. The resonance.
Exactly. And so for our sort of situation where we have kind of two planets orbiting a star interior to this disk, we would expect that outer planet, the one that's closer to that inner edge of the disk, to have a much stronger precession rate than the inner planet.
Okay.
And so that's kind of the general case we'll consider.
Okay. Good. Good.
And if that's true, say the outer planet is much stronger than the inner planet, precession rate-wise, then the difference in the precession rate is also high.
Yes.
So there must be a large differential precession rate in these sorts of cases.
The large difference shows up right there in equation 7.
Exactly.
Yes.
And if you can make that large, well, maybe you can make this blow up. That's interesting.
Right. Exactly. Yeah. Hit the pole.
There you go. And so that's the conceit. Now we've kind of cheated a little bit here. I'll go back to kind of equation 2.
Okay.
One of the things I didn't emphasize is that this sort of approximation works best when your eccentricities are pretty low. This is a first order approximation in eccentricities.
Okay.
And then I've used this to derive an expression for when the eccentricities get very high.
Magic happened.
And so that's, potentially objectionable. That doesn't seem very reasonable.
Magic happened. I don't know.
And so if we want to, confirm that this effect is real, you want to do n-body simulations.
Okay.
It's not really good enough to just do out this analytic mathematics and get this result, because
but informative if it works.
Definitely informative. Gives you a hint that something might be there, but I don't think this is conclusive on its own.
Okay.
And so the next thing we did, do some simulations of these resonant capture situations. We use Rebound, standard astrodynamics library. It's free for anyone to go download and play with. I did as an undergrad. It's a lot of fun if you like astrodynamics stuff. And we just set up two planets around a star and ran through the same sort of convergent migration capture sort of physical situation.
And the potential of the disk that's what they're moving in.
Exactly.
Okay.
And we incorporated that by just adding the precession rates directly so that we didn't have to spend time, simulating the disk or doing any of that.
Oh, no, understood. Just wanted to make sure that was clear to me. Okay.
Yeah, definitely.
Okay.
And so you can do this pretty fast because it's just n-body. You're not doing any hydro or anything like that.
Right.
And we got our potentials from that expression earlier.
Yes.
And so that's easy to do, luckily, and you can do this in mass for many planets.
Yay.
And, we're doing resonant capture simulations, so planets have got to be migrating, there has to be some eccentricity damping, and then there's the additional precession associated with that. And we can do all of that with Rebound X.
All right, cool. Yay, Rebound.
I mentioned that we're migrating into these resonances, and they have kind of simple period ratios. So we choose an arbitrary resonance, one of the stronger first order ones. We use the 3:2 resonance.
Yes.
And we pick some masses for the planets, and we assume our star is a solar mass.
Okay. Scale to solar.
So fairly, I guess, reasonable assumptions. This is kind of typical of what you might see in exoplanetary systems. They vary by like an order of magnitude in every direction, but you could do worse than this. These are not Jovians or a B-type star or anything like that.
Okay.
So we pick some reasonable planet masses and we migrate them into resonance.
Yeah.
And once they capture, reach equilibrium, we get rid of the precession. And we do that to simulate a process called disk dispersion. We know protoplanetary disks don't stick around forever.
Okay. Sure.
So sure, they migrate into these weird configurations, but what we observe is the planets after that has all dispersed, the whole drama's over.
The clearing out phase. Yeah.
Exactly. Yeah.
Okay. With you.
So they're all kind of two-part simulations. First, let's test this inward migration, how that depends on precession rate.
Right.
Then let's clear the disk out and
know.
check how the system as we would see it today is affected by those precession rates.
Cool. I'm with
So
you.
we're going to do both.
Nice, nice.
Now, the first case of this is shown in figure 2.
Here we go. Yeah, we turn off migration. Yes. Figure 2. Let's go to figure 2 and take a look at the simulations. Bang. Okay.
So this is a simulation run at a pretty low precession rate. The planets are, significantly perturbed from equilibrium, but nothing extreme is happening yet.
Yeah. Yeah.
Kind of divided into 2 parts. This part on the left, we have kind of the eccentricities rising. They seem to asymptote to some value.
Yes.
Looks like they're equilibrating.
And
We have these kind of resonant angles right below it.
okay.
Those look like they're reaching some sort of equilibrium. Seems reasonable. Seems compatible with kind of traditional theory.
Okay.
Then we've got this dotted line in the center here. That's when the disk goes away. So the planet's migrated into equilibrium. They're in that equilibrium state for quite some time.
Scale because that isn't there. Okay, I'm with you. Yeah.
Yep. Good old dynamicist. We love rescaling all of our variables.
Okay, it's fine. I get it. I'm with you.
It makes it very difficult for anyone to understand what's going on, but it also makes all our results more general.
Yes, it does.
So it doesn't matter what P2 is, what the period of the planet is, it's
right
in whatever units are relevant to you.
Correct. Okay.
Double-edged sword, unfortunately.
Mm-hmm.
But once the disk disperses, we start to get these big oscillations in eccentricity, and the corresponding resonant angles start moving around as well.
Yep. Bang, bang. Yep. They start bouncing around.
And the way to think about this is, we have one equilibrium point that was kind of set by the, that was shifted due to the precession.
Yeah, right.
And then suddenly the game changed when the precession went away.
Yes.
And now the old unperturbed equilibrium point is really where the planets would prefer to be.
Yeah.
They can't be there anymore. There's no more dissipation in the system. So they end up orbiting about that old equilibrium point.
Okay, okay.
And so it's just the equilibrium shifting that's kind of doing this.
Okay.
So you get these large eccentricity oscillations that's potentially observable. And you also get these non-zero libration amplitudes. You can see theta starts bouncing up and down.
Yeah.
And that's something we see in some exoplanet systems. We see they don't always damp all the way to the equilibrium point. They don't always make it there. Sometimes there's oscillations left over.
Okay, cool. Very
A lot
good.
of different explanations are given for this. This is one plausible mechanism where you could generate those libration amplitudes.
Nicely said. Okay. Very
Now,
good.
if we go to figure 3.
Figure 3. Figure 3. Okay.
The same style of plot, but a much more extreme case.
Okay. Okay. Oh, yes.
So this is odd. So here we've turned up that differential precession rate really high. This is an experiment. Let's see what happens. We still capture into a sort of equilibrium on the left. But note the eccentricity scale here is totally different from what we were dealing with before.
Factor 10.
Very much so. This seems to be capturing at an equilibrium eccentricity of like, what, 0.75, 0.8?
Yeah.
That's very strange. It seems reasonably stable. I've carried on this simulation for, what is that? Almost 1 million orbital periods.
Yeah, that's pretty flat. By eye, that's flat.
Yeah, that looks like a stable configuration. How strange. Once the disk dissipates, things go haywire, as you might expect.
Boing, boing, boing.
No more eccentricity. This is only carried on for, you can see on the x-axis, about 50 orbital periods.
Right.
If I kept going, that would almost certainly result in scattering, a planet gets ejected, something like that.
Changes, yes. Okay. Okay. Ooh, yes. Wow, look at that.
And so now we have to kind of ask ourselves a final question. We know things kind of behaved normally. Looks like a small perturbation to traditional resonant capture theories when the precession rate was small.
Right.
And if we make it too big, something crazy happens.
Those, yes.
And so you might ask yourself, we don't see planetary systems like this with, giant sub-Neptunes and these highly eccentric orbits, at least not in multi-planet systems.
Right. So
what's the critical precession rate?
Okay.
If we're not seeing stuff like this, then, this probably isn't happening.
So where's the onset, right?
Yeah. Where does this
critical value? Yep.
And so to investigate that, we ran a whole bunch of these simulations that's shown in figure 4.
Okay, let's hop on down and take a look at mini. Figure 4. Ooh, nice.
And so we've got this pretty rainbow here. Blue is low precession rate. Red is high precession rate.
Yes. Yep.
And now we're showing everything on the same scale.
Cool.
Yes. So these kind of blue trajectories are similar to the system we showed in figure 2.
Yes.
And these kind of red trajectories are more similar to what we showed in figure 3.
Yes. Okay. Wow.
And so we can see the transition between these blue-like trajectories and these red-like trajectories is actually pretty sudden. Yep. It kind of just turns on suddenly between low eccentricity equilibrium and high eccentricity equilibrium. So it seems like there is, in fact, some critical kind of differential precession rate. And if you go beyond that, you end up in this very high eccentricity regime where you're scattering planets and presumably the systems we see today with Kepler and TASS did not go down that path because they're in nice, neat resonances. They're not scattered everywhere, right?
Okay.
And so you could turn that around and see that as a constraint on the masses of disks that must have led to the systems we see today.
Cool.
They were too massive, then they would have gone up this high eccentricity branch, they would have scattered, and we wouldn't see those planets as we see them today.
Cool, nice.
We'd see, 1 or 2 planets and weird orbits around a star, the traditional signals of scattering.
Very cool. Gotcha. And so we would like to know, what is that critical value?
Yes, indeed. Which brings me to kind of the final figure I'll kind of make a point of talking about in this paper. That's figure 5.
Okay.
Here I'm showing the precession rate on the x-axis, equilibrium eccentricity of that inner planet on the y-axis for various values of k. So that's various types of eccentricity damping. Ratios of eccentricity damping to period ratio damping. And then we've got a bunch of different types of dots here showing the relative eccentricity damping between the outer planet and the inner planet. So you might expect maybe the outer planet gets damped more, it's closer to the disk, there's more circularization. Maybe you don't believe that, maybe you believe they're about the same. Could be reasonable. And what I'm showing here is, regardless of what you believe, regardless of the K you pick, there seems to always exist some precession rate where you suddenly transition from these low eccentricity equilibrium to these high eccentricity equilibrium.
Yes. Cool.
All these curves just look like scaled versions of each other. This is not something that was particular to how we initialized our system. It's not strongly dependent on the parameters you choose. This seems to be a general thing.
Yeah, the features are similar, yes.
Pick your eccentricity, pick your eccentricity damping ratio, pick your planet masses.
And
you're always gonna run up a cliff at some point.
At some point, yes. Wow.
And so that was the main result of this paper. It's
Cool.
this idea that the mass of these disks really do shift around your resonant equilibria. Their dispersion can lead to, oh, sorry.
Quite a bit.
Yeah, quite a huge amount in some cases. If you can drive that precession rate high enough, that means that out there in the exoplanet population, there may be signatures of this process. And if you can spot those signatures and properly run a regression on them, then you get something really valuable. You get a clue into the mass of that disk that was doing the perturbing initially. And that's very exciting. It's not a lot of ways you can get that.
Very few. Very cool. Very cool.
Very technical paper, but hopefully I managed to communicate
thanks to your wonderful explanation. It's all very clear. At least it's clear to me.
I'm glad.
Oh, good job. Good job. Zach, I want to thank you so much for walking us through your very awesome article. Thank you.
Appreciate it.
Yeah. And you kind of hinted at it a little bit as we went through. And so let me push on it a little bit and ask, where do you think we go from here, given the published article? Are there additional terms that one could put in the Hamiltonian? Or is there observational campaigns to look for the predicted effect? And just sort of, next steps, where do we go from here? And so on. So.
Absolutely. I think this is a very exciting field. It's just kind of starting to take off, this subfield of resonant inquiry and using that to figure out what's going on in these planetary systems. I think there are a few things that need to be done. Firstly is the typical question people ask when you tell them about resonant capture. So they think about it for a little while. They say, well, why aren't all planets in resonance?
Okay.
Migration seems pretty common. Damping disks are common.
Okay.
Everything should be there.
Okay.
And it turns out there's an instability that prevents that. And we see signatures of that instability in the exoplanet population.
Okay.
We don't know how it varies with precession rate. There may be additional information there that we could pull out that we haven't taken advantage of yet.
Okay.
So there's a theoretical angle that needs to be explored further.
Cool.
So far as fitting goes, recent work has shown that fitting libration amplitudes is more complicated than anyone thought. You can get biases if you're not careful.
Okay.
And so that needs to be resolved, and proper libration amplitudes need to be tabulated before this sort of work can occur, kind of on a large scale.
Okay. Cool. Good. Well, it will be very exciting to see this develop over the next couple of years. Very cool.
I'm looking forward to working on it.
Yeah. Dr. Zach, yes. Absolutely. So Dr. Zach, thank you so much for walking us through your very lovely article.
Absolutely. Happy to be here.
Yeah, and that will do, everyone. And I hope this makes your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.